Okay, folks. Today we had no introduction. We went directly into what we had to do. I got my son on the other side here, and I'm going to ask him to come over because some people think there is no such individual. That I'm kind of a ventriloquist or something. I don't know. I mean, what do people think? Come on over. Show your face here.
Half asleep, everyone.
This is my youngest son. Okay, so he's alive. He's not God. I'm not a ventriloquist. This is guys for real. He looks a little different than me, but yeah, he's in the background there. Okay, so just so you know that there is a guy named Adrian Gady out there. He goes by Ons. We don't know why, but I guess it had to do with onions.
Long story.
Long story. Well, we have time.
My brother couldn't pronounce my name when we were little.
Oh, is that what it was?
That's the short version.
Okay. Anyways, what's today? Today we have gluons. You know what a gluon is? Nobody does.
Well,
But maybe someone can tell me, you know what a gluon.
It's what's in Elmer's glue.
Yeah, Elmer's glue worked with gluons. They get things to stick together. And yeah, we're going to learn a little bit about gluons today, what they are. But let me give a little introduction here, a little intro. There's a fellow out there, name is he goes by the moniker Draft Science, and he's been looking at the videos lately, and he's criticized them and so on. And the reason I mention him is he proposes.
What videos did he criticize?
All of them. He's been following any video that I put up. He kind of
your videos.
Yeah, no, and not only that, just the real physics ones and so on. So he's criticized them all. And well, what's his bitch? What's he got against them? Well, he proposes particles. Now that's a novel one, right? Nobody's heard of that before. But he wants to produce pull through push. That's where we have a little bit of a problem. And for those of you who saw the Real Physics number 3, the third video, I'll just put that up there real quick. Here's the first one. It shows that cassemer, that's the fellow there. I call him cassemer for the cassemer effect. I love that cassemer effect, so I've named him cassemer. From now on, that's what I'll refer to him as cassemer. And cassemer here is producing pull by throwing stones at the poor donkey, okay? And that's the quantum version. Essentially, it's what was the fellow's name? Japanese guy, Ikawa. That's the Ikawa effect. He's got an equation that just puts a negative sign and says if you send a force outwards, it brings the object inwards. Okay, and he does that with a negative sign. Now that's quite magical, you know. He just puts a negative sign and Yukawa and he pulls the donkey in. And Yukawa, you know, I think he got a Nobel Prize for this. So it gives you an idea of also how valuable those Nobel Prizes are. You know, this is what this guy comes up with. He got an equation with a negative sign that pulls the donkey in by throwing stones at it. Okay, that's the quantum version. What does Mr. Draft Science propose? He proposes the following. He proposes that if you remove, well, he doesn't exactly. He says that I'm raising a straw man here, but the general idea. This is the cassemer effect that you're seeing here. That's Mr. Cassemer there. And what you do is you remove the matter between two objects, and the two objects come together, pushed by the pressure of the matter outside of them. Okay, so this is a mechanism that's called the cassemer effect. That's why I labeled my little guy cassemer. I love that. And you know, that's what they propose for two plates which are electrically or I guess magnetically attracted to each other simply because you remove the matter between them. Okay? So that's another way of doing it with particles. And then, of course, we have the quantum way, which is the Bowl way. You know, you've got this warp space, and it's like a roulette. You know, you have the little ball on the roulette, and you just have a wall of this depression that prevents you from flying out of the solar system. For example, the Earth or the Moon or whatever. We can't fly out because there's a bowl in which we are rolling around. Okay, and so that's the other effect. So we have the three effects. We have the throwing stones, one right after another. Here's the rolling stones or the throwing stones. We have the pressure. We remove matter between them, and we have the bowl, and that's warp space there. And the sun weighs the warp, the space down, space time. Really, it's a four-dimensional concept here. It pushes it downwards, and the Earth has no chance but to roll around the bowl. Okay, so those are the three mechanisms of attraction. And of course, what we're proposing is that all atoms are interconnected, and the Earth just swings the Earth around. Now, why am I mentioning? Huh? You missed something or what? Yeah, go ahead. Ask the question. Throw me whatever you got.
All atoms are interconnected now? Is that a fourth?
I didn't show that one, but yeah, the Earth, I should have shown that maybe. The sun twirls the Earth around because all atoms of the Earth are connected to all atoms of the sun.
That's the fourth.
That's the fourth, and you'll see it in the third video. I didn't show that one. I didn't want to brag, so kind of left it out. But everybody that seen my videos, they understand what I'm talking about. Why am I bringing this up? I'm bringing all this up because these are the three mechanisms that are being proposed for attraction.
You mean fourth?
Including mine would be fourth, yeah. But the issue is these are, as far as I can see, maybe there's some other one out there, I don't know. But these are the mechanisms, the physical mechanisms being proposed for attraction. Okay, so whether you talk about gravity, you talk about magnetism, you're talking about attraction, and these are what people have come up with over the years. They said, look, you remove the matter, they come together. You throw stones, and they deliver negative momentum, okay, attracts it. And the other one's the bowl. You can't get out because even though you have this centrifugal motion of the Earth or the Moon or whatever object, celestial object out there is revolving, I can't get out because there's a bowl caused by the depression of mass weighing down space-time.
This is a really good way of doing this, kind of laying out all the different forms of pull.
Yeah.
Kind of multiple choice question.
Yeah,
okay, what we have only so many. Which one is it?
Yeah, and that's what the third video says essentially. It says, which one would you propose for the workings of the universe, for how Mother Nature runs her shop?
Because there's only so many. And
yeah.
And it's very few.
And we discussed that the other day. There's maybe 10 at most that you can dream of. You can put angels in there, maybe, I don't know, a couple more. I don't know. I don't think they even get to 10. Yeah, there's only so many forms of contact you can imagine. And the problem with particles is you have to do it through push mechanisms. You're creating pull through push.
Well, let's go through the three.
Well, those are the three. The three are the throwing stones. That's cassemer throwing stones at the donkey. We have the pressure. You remove the stones that prevent you from getting closer to each other. And you have the bowl, which is essentially mass, because it's not even matter. They call it mass. Mass weighing down the canvas of space-time, and you slide towards the other guy. The only reason the Earth doesn't slide like cassemer and the donkey there is because it has this centrifugal motion from its orbit. Okay, so the orbit, the centrifugal motion, wants the Earth to leave the solar system, but the fact that we have a bowl creates a bowl, a wall, and the Earth can't go through that wall. The funny thing is that we send probes to the Moon and to Mars, and they have to go through that same bowl. And you have also asteroids that come in through that bowl, or comets and so on. And the question is, why can they go through there, not the Earth? So that's a question.
That's not the biggest problem. The biggest problem.
That's the food for thought. I mean,
That's not the food for thought. The biggest problem with this is you still have something pulling it down. You haven't
but
solved the question.
well, let's see. You're saying pulling it down, but remember you have the centrifugal motion of the Earth, the fact that it's rolling around and it's trying to get out.
Holding it down.
Yeah, well, what holding it down is mass, right? That's what they say.
Yeah, but that's my point. It's holding it down. You need some. You still need that pull effect. You still need a pull mechanism to explain why it's touching.
Oh
the
yeah,
canvas.
that's been criticized quite a bit of relativity. The fact that relativity relies on Newton's force. You need that force to weigh the canvas down, because the question is, why doesn't it weigh it upwards?
And even if it did, you have to answer why does it touch the canvas at all? That's the question.
Yeah, and again, why don't probes going to Mars? Why can they perforate this wall?
You'd have to say it maybe the canvas is sticky and it like glues to the Earth. No, but that is what you'd have to say. There's something adhering the globe.
I'm getting to the gluon, right? To the glue.
But there's no other way to talk about the bowl. You'd have to say, okay,
the
Earth is stuck to this canvas.
Yeah.
It's not being pulled down, it's stuck to it. That would be the only way to say that.
And again, the mathematicians dismiss this as a straw man. They say, oh, you're attacking the physical interpretation. Yeah, that's what I'm attacking. That's physics. And they say, well, no, physics is mathematics, equations, numbers. And the numbers, the equations, that's what they lead us to believe, that there is some kind of four-dimensional canvas that we can't imagine. And the Earth, the sun first weighs it down, and the Earth rolls or slides around this. And that's the mechanism they propose, and they don't allow you to publish something saying it's irrational what you're proposing. They won't allow you to publish something like that. And I wrote a couple articles lately about this in Quora. And that's that you're not allowed to criticize the physical interpretation. You want to publish something, come in here with your equations, your math, okay? And anyways, why am I bringing all this up? Well, because we have this Mr. Draft Science, and he's proposing, pressure. He's proposing the cassemer effect. And I'm not sure exactly all the details, because he's a weird kind of guy, but he's proposing that somehow you remove matter. Or he says even the matter stays there, but there's more pressure from the outside. I don't know how he conceptualizes that. The bottom line is that he doesn't recognize the force of pull in the universe. So if you pull on a donkey, he doesn't recognize that. He says that a donkey is being pushed by the matter that pushes from his tail, not from the rope that's pulling from his neck. So he doesn't recognize the force of pull. Maybe here on Earth he does, but not out there in the universe. He says, no, the force of pull doesn't exist. The way you produce pull is through push. Matter pushing objects together.
Wait, but it's all right to say that it exists on Earth, but not in the universe?
And that's the point. The point is that one of the things quantum will never answer, and Mr. Draft Science will never be able to answer, is the force of pull. And that's the issue. And if you sidestep that, you're just eluding the issue. Mm-hmm. The issue is you have to answer the force of pull, and for that you need an elongated mediator. And of course, since they can't dream up of one, they say, no, the force of pull doesn't exist. We do it all through push. And he's not the only one. There's a lot of people out there. One of them, a guy I had a discussion with, Tom Van Flandern. He's dead now, and I had a telephone conversation, which I recorded, by the way. And he proposed push mechanisms for gravity. They called it push gravity, and that's the reason for that is that all these people want to do everything with particles, but they say, well, then how can we produce pull with particles? And the only thing they could come up with is the cassemer effect. The cassemer effect is famous because Mr. Cassemer suggested remove matter between two objects and they're pushed together. That's essentially the mechanism.
Well, that's because they didn't talk about the flat Earth version of gravity, which I think.
Oh, we have a sixth one. Okay,
yeah,
come on.
It's a way better one than all these.
Okay, I like that. Come on. What's it I like?
Basically, in a nutshell, the Earth is the bottom of the universe, right?
Okay, let's concede that
I
assumption.
don't know what's under us, but let's not talk about
We're
that.
hell.
Whatever.
Everything else is heaven.
But basically, the universe, I guess, is a tube. But whatever it is.
Okay, we're at the bottom of
and we're going up at 9.81.
9.8 meters per second squared. Yeah.
So basically,
we're going up.
Yeah, we're accelerating upwards.
Okay,
like being in a train.
For whatever reason.
Yeah, it's like being in a train that's always accelerating. So
okay, so it's coming up.
You always feel that it's a push mechanism for gravity.
Yeah. Okay,
we're
but
being pushed up.
What's that got to do with? Oh, we're pushed up towards the objects.
Towards the heavens, yeah.
But when you drop a pin, here's a pin, and I let go of it and it falls downwards.
Yeah,
and now
because
what is the Earth coming up?
Yeah. That's the explanation, which I thought was very clever.
The Earth is coming up towards the pen.
Up towards the pen. Nothing's falling. Everything's being.
Okay, fine. Let's concede that just to understand what the guy has through his mind. So he's saying the Earth is coming towards the pen for whatever reason. Okay, it's being pushed by an elevator, for all we know, a lift, as the British would call it. Okay, so the lift pushes the Earth up towards the pen when I throw the pen. So the Earth comes up. What does that do to me? Because the pen. Thing. No, but I'm staying here. I haven't moved.
But you are moving.
No.
What do you mean?
No, listen. My relation to the floor, my relation to the floor is the same, right? That hasn't changed. What has changed is that the floor has come up towards the pen, but I'm still stuck to the floor.
Oh, because you're already on the floor.
Yeah, but see, the floor hasn't come up to me. It came up to the pen, but not to me. That's what.
But that doesn't solve it.
No. But I'm trying to understand. I'm trying to understand why the floor comes to the pen, but the floor doesn't come to me.
But you are at the floor. If you were in the sky, you'd hit
no,
the floor.
No. But the pen is falling with respect to me. I can see the pen falling with respect. I haven't moved with respect to the floor.
Yeah.
So the pen is falling towards the floor, but these people are saying the floor is coming towards the pen, but that can't be true because if the pen, with respect to me, right? The pen is over here, right? And here I am. So the floor should come up here and should squash me.
No. It's just like in a train.
Okay.
You're in a train that keeps going faster forward.
Okay.
Well, it's hard to think about it without gravity, but if you let go of something, it'll go without you. It'll go.
If you stop the train,
no, not stop the train. The train keeps going faster and faster.
Okay.
And you throw a ball in the air.
Okay.
The ball, it's not going to fall back into your hand.
Right, it curves.
Yeah.
Okay.
It's just like that. You're still moving, but the ball goes on because you're touching the train.
Yeah.
So
now put that in this situation.
It's the same thing.
Here's the pen. I dropped the pen. I'm just letting go of the pen, right? Boom. I stayed where
we've seen gravity before.
Yeah, now as far as the camera doesn't lie.
No, but you feel the acceleration of the Earth.
Forget about acceleration of the Earth. I'm saying, if the pen fell, and you're saying no, the pen does not fall. The pen stays here in relation to me.
Yeah.
The Earth came towards the pen.
Yeah, and you.
No, it can't be both. That's the point.
It is.
No. But I'm trying to make that point. I'm trying to make the point that the Earth can't come upwards for both of us in the same way because
it can.
No, hold it. Let me finish.
Touching the ground.
No, hold it. Let me finish.
I don't know why it's so hard.
No, it's terribly hard for me. I'm from the 1950. I was born in 1952, so I have a slow mind. Please forgive me. Here's the floor. What's the distance from the pen to the floor? Let's call it 1 meter.
Yeah.
And my feet are touching the floor, so let's call it 0 meters or half a centimeter, whatever, a very small distance, right? Much less than 1 meter, right? So the floor comes towards the pen, but the floor doesn't come towards my nose.
Yeah, it does. But
no, it can't be
touching the floor.
You're still not getting what I'm asking. It can't be that if the pen stays at the same level as my nose, the floor would come towards the pen and my nose simultaneously, and I would maintain the same relation.
Yeah, but your feet are pushing your knees, are pushing your hips, are pushing your ribs, are pushing your nose. So you're being taken up.
Yeah.
As the pen, there's nothing holding the pen up.
And
holding
is the
pen
fluid
in-
coming towards the pen?
Yeah, it's coming
If
to
the
the pen and your nose, but there's things that are relaying the motion of the earth into your nose so that your nose can never touch the ground, because essentially the earth pushes your feet, pushes your knees, it's like you're being taken up while there's nothing that's taking the pen up.
No.
The pen just
We
falls.
got a problem. We still have a problem, no matter what you say. If the pen is at the same level as my nose, I have a big nose, so I think that's
Easy
a
to
good.
see, easy to
Yeah,
spot.
it's a good relation, right? Good level. So if the pen is at the same level as my nose,
Yeah.
the earth, the floor should come simultaneously at the same distance to the pen as to my nose. Why not?
Because
What-
your feet are pushing your nose
Yeah,
up.
but then the pen obviously is not at the same level as my nose when it falls to the floor.
Yeah, because your feet are pushing your nose up.
No, but I don't care why. I'm saying that the pen is not. It's a fact. It's a fact that the pen is not at the same level as my nose. The pen is closer to the floor than my nose now.
Yeah, after time, yeah.
And so the question is, why has that happened if the floor came up to meet both my nose and the pen?
Because your knees and feet are pushing your nose up.
Yeah, but I don't care about the
It's
why.
like putting a broomstick on the ground, right? Standing up broomstick. Obviously, the top of the broomstick isn't gonna touch the ground anytime soon, because the
Why?
rest of the broomstick is holding it up.
Yeah, but if the floor
like
is
it's
coming,
already touched.
no. But if the floor is coming up, it should push the broomstick up. Also,
It
that's my
does.
point.
It pushed.
No,
it
but
does.
that's the point. It doesn't.
It does.
No, it doesn't.
Just
because
like you, it's pushing you up.
it's pushing me up. Okay, is it pushing the air up? Next. Okay, you're right.
Yeah.
I see what you're saying. Okay, is it pushing the air up next to
Yeah,
me?
I think that was the.
Because
that's
if
how
it-
it holds airplanes up.
Yeah. I mean, at some point, there's got to be some
Yeah, it pushes
some
the air
problem
up.
there. You know.
No, it pushes the air up.
Okay, it pushes the air up. Why does it push the air, and why does it push me, not the pen?
Because there's
I mean, why does it push the air together with a pen up?
Because
Why
because
does
the
this go
pen-
through the air? Why
because the
why do
pen
I
is-
go through the air?
because-
Why don't I go through the air?
because the pen is heavier than the air.
So am
But
I.
they get weird because they only talk about like density. They also say there's no like. Yeah, they get weird with it, but the way I understood it with my logic is the pen is obviously heavier than the air,
Okay.
so it essentially the air just goes around it.
The air goes around me too.
Yeah, but you're still touching the ground, just like the broomstick. Yeah, the air goes around you.
Yeah, but see, if you put a broomstick, that's an interesting point. If you put a broomstick, here's a broomstick, we'll call the edge of the frame of the, that's where it's standing. It would push it up as well.
Mm-hmm.
So they have a logical problem
No,
there.
they don't.
Yeah, they do.
That's the thing. The only problem they have is there's no reason why the Earth is going up. that's
No.
the real
That's
issue.
one issue, but there's another issue, and that's that. See, if you're going to treat the unseen things like air, and you're going to treat them as nothing, and say, well, it doesn't really push the air up, or it does. Well, okay, let's assume it does. The point is, if it pushes the air up, it should push the pen up as well.
No, because the pen is heavier.
Yeah, but then
So normal rules apply where the pen goes around the air. The air goes around the pen. Heavy things still.
There's something wrong there, Yubs. Anyways, I'll take
Yeah,
that up, but I'm sure there's some.
We're
Yeah.
still back to is there a pull force? Is there a pull force in the universe?
Yeah, the issue's pull, and why is pull important?
Is everything just push? Could you?
Right.
I guess that's the better question. Could you explain everything with push? Since push is self-explanatory, and no one has to explain
And you
why
can do-
one domino makes the other one fall.
That's one issue. The other one is you can do it with particles. You
Yeah,
can do all of it with
you
particles, and
can
that's
do
why.
everything with-
And since they do particles, they say, "Look, we can't explain pull, so let's do it all with push,
Actually,
and we'll do it."
That's kind of interesting. That push is self-explanatory. We can all understand one thing touching another and transferring its motion.
Pull
to
is
the
not
next one. But
self-explanatory.
pull apparently isn't.
Well,
pull is
if
more magical.
like I showed in my, unfortunately I should have done that. Put my pull of the donkey, but I didn't do that. But the question is, we can all conceive of pull very easily, and everybody can understand. It says, if you see something in the horizon out there very far away, and you see a farmer pulling on a donkey, and you can't see with what he's using, you're saying, what's he doing this with? Magic? But when you get up closer, you say, oh, he's pulling on a rope. I couldn't see it from back there, but now that I see the rope, but then everybody understands it. It's self-explanatory.
Even if you didn't see the rope and you just saw the motion,
you would imagine.
You would imagine the rope.
But that's from experience.
Is there any? Well, I guess
that's from experience.
I can pull an object without a rope too.
Well, you're using your arm, which is an extended object.
No,
you always need an extended object.
Does that count? Is it just a weird push?
No. But what I'm saying is, what I'm saying
is pulling even with a rope just a strange form of pushing.
No, it's not, because
what's the difference between pushing a donkey and pulling it on
a donkey? The difference is that in one case you're using an elongated mechanism, a medium, right? As a mechanism, whereas the other one, you don't need the elongated mechanism between them, you need one outside of them.
But it doesn't have to be elongated.
It does. Oh yes, it does. I don't know of any. Give me an instance where you don't need an elongated, rope or cable or whatever to pull on something.
It depends on what you mean by elongated.
An elongated medium. I mean, what do you need? An extended medium, something like a rope, a chain, something that's long between them. Not only long, but between them. It's got to be between.
If I glue something to my hand.
If you glue something to your hand, yes. Go ahead. And
that's a pull without an
okay, but you do have
it's just stuck together.
Okay, but you do have it between, not outside of.
Yeah.
Okay, I caught it. It is elongated at the microscopic level because the glue is not, there is some.
It's seamless. I think that's the right word.
Seamless.
There's something touching my hand and touching the other thing. There's no
no interruption.
There's no
interruption. Okay, yeah, and that's seamless. Yeah, maybe you don't need an elongated one, I guess, but that's only when there's contact. That's a special situation. What you're mentioning, the glue. The glue is a special situation
but
where touch
basically covers all the pull bases. Seamless. Because you can't think of a pull thing that isn't seamless. There's no such thing as discrete pull.
Now you know why my son is my son. He's an intelligent guy. He comes up with all these weird scenarios, which I hate him for, but you gotta give him credit for it. Yeah, okay.
That's pull versus push. Push can be discrete. Push is always discrete, actually.
Whereas the other one is seamless, but seamless has to be clarified because glue, let's assume glue is made of particles, just for the sake of argument, okay? So we have corpuscles between your hand and the wall.
Yeah.
You're going to pull on the wall or whatever. It could be a piece of carton. You pull on it, right? And you pull on it. But hold it. The pull mechanism is here. Not here.
You can glue it to your back too.
No. But let's get that straight.
To the front of me and
that's why I put elongated because here you can treat these two as one object.
No, because again I can just glue it to my back. My back isn't elongated.
Yeah, it is elongated. It is. It has a certain It has a certain elongation. You're okay. What's pulling? Give me the whole scenario of your back pulling on the wall or on a box.
My muscles, I guess.
Yeah, there's some elongated thing involved. No matter how you can't avoid it.
You could call anything elongated then.
Well, elongated means it's longer than it is. It's pulling in the direction in which it's long.
Yeah,
that's
my back is long parallel to it.
Correct.
The other way.
That's my point.
Wrong. The other way. My back is this way.
No. Your back is whatever it is from your back to your heart to your front to your chest. That's the elongated part. It's what you said. Parallel to the direction of motion. That's what I'm saying.
But this is perpendicular.
No, it's
because
not.
My spine goes this way.
Okay, because you're looking at it that way. But where's the pull from? The pull is in the direction. Elongated in this direction. And
elongated because you could do it with non-elongated objects.
You'll never find a case.
My back.
No, because your back extends. Because it's not just you can't just talk about your back, just the sheet, the skin that touches the cardboard. You can't just do that. You say, look, what is my back? Well, it's just the skin, the finer out surface of my skin. You can't do that.
Okay, how about two atoms that are touched?
Because the surface is not just.
How about two atoms that are connected, like two two atoms in my
What
skin,
are they connected by?
They're just touching.
Yeah, no matter how you look at it, there's got to be some elongation, some extended object there.
The back thing isn't really elongated, though.
No, it is. The problem is that you're using the word back, and you're saying, well, my back is up and down, not, longitudinal. But we have a problem with that, because really when you're using it, you can't say your back is just the outer skin, and that somehow that outer skin is pushing you forward. It's not just the outer skin. It's your legs that are pulling you forward, and you're saying, my back is pulling the carpet. No, it's your back is a little longer when you use it in that context.
I think I'm just too sleepy to give you a curveball here. I'll let you go this time.
Okay, thanks. I got off the hook easy this time.
So wait, what's the difference between pull and push?
Okay, I'm saying that first you need elongation. He's going to have to think a little bit about it. I'm going to think a little bit about it as well. Not as much as he will. But I think you need elongation. But I like the fact that he says that you need, what was it? Uninterruptedness, seamless.
Yeah, uninterrupted.
You need some kind of uninterruptedness there. Okay.
I think that's literally what defines pull versus push. Push
But
is always discrete.
But
You
isn't
can't push something with a rope.
uninterruptedness a synonym for elongation in that
It
context?
could be.
Yeah,
But I'm saying with
that's what you gotta
with
think about.
push, it's literally the opposite. You can't push with a rope.
Yeah, well, you can, but
You have
it's
to ball it up. And
right.
it's
No,
discrete.
no, not like that. You torque it. See, here's you got a rope, right? And in fact, that is the mechanism for, which I propose, because they say that light travels as a wave and arrives and
that is a
departs
push.
as a particle. What's the particle part? Well, here you have the rope. Let's get it right. And which one is okay? This. So when I torque the rope, let's get the little part out there. When I torque the rope, here's that motion there, right at the end, and that's the push. That's the particle nature of light.
True.
When it hits the atom, when it enters the atom, when it forks into the electron shell and the proton dandelion.
So you can actually have seamless push as well. Or
Yeah, right.
push.
What I'm saying is, the torsion of a rope creates that sensation here, that thump, that signal, right when it meets the atom. So that's where the push occurs. So you can push with a rope, but the point is that a rope, primarily, when you look at it, you think of it as an elongated pull mechanism. You don't want to pull on the donkey. You don't throw rocks at it. You pull on it with a rope, and that's the point. Now, I mention all this because what is the context? The context are the gluons. And this really will blow your mind if you're not familiar with gluons. But gluons, there's, let's start at the beginning. A proton and a neutron, according to the establishment, according to the mainstream, right? Quantum mechanics, according to the particle model, the standard model of quantum mechanics. A proton and a neutron are made of 3 quarks. 2 down, 1 up, 2 up, 1 down. I don't care about that nonsense. The point is, you need 3 quarks. What are 3 quarks? Each one is a ball. So with 3 balls, you make another ball. Now, that's the first problem I've got with it. I challenge you to go home, take 3 balls, put them any way you want, and see if you can create a ball with that. And you can't. And so what they do is they artificially put a globe around the 3 balls and say, look, these 3 balls make up the proton or the neutron, which is also a ball. Okay, so we got a problem there already from a structural point of view. But let's forget about that. That's trivial. Okay, I don't care about that too much. Here's the real argument. The real argument is that why don't the quarks leave the neutron? Why don't the quarks leave the proton? Why don't these balls just fall off? What keeps them together? And what keeps them together is a particle they invented known as the gluon. Okay? And so what is a gluon? This has got to be a really magical particle that keeps quarks together within the proton and within the neutron. And so here are some images. I want to put these up there because a picture or a video is worth 10,000 words. And here's one. Here's the most important one, okay? This is number 1, okay? This is from CERN. This is the accelerator in Geneva, Switzerland. Probably number 1 accelerator in the world. And this is their official stance on what a gluon is. And I want you to focus on the particle nature of the gluon. See if in any way you think of a particle when you see a gluon. Here's the gluon. Okay, so we have the quarks, which are the three big balls, the blue, red, and green. And what do you have? You have the bed springs. That's what I call them. I call them bed springs. And those bed springs are the ones that keep the quarks together from flying apart. And the first question comes up is, what do you mean gluon bed springs? I thought quantum was a particle theory. You know, what is a particle theory? The quarks should be throwing particles at each other, and those particles somehow, by some kind of unimaginable mechanism, keeps the quarks together inside the proton. What these people are illustrating are bed springs. And yeah, we can all imagine that, you know, if you put a bed spring between the quarks, they're not going to fly apart. And you can all say, oh yeah, I don't need to go to college. I can understand it just by watching this picture, this movie.
Gluons are bed springs?
Well, I'll get into that in a minute. I mean, if you look at that, you would understand the mechanism. You would say, okay, the picture is worth a million words. I can understand it clearly. What these guys are saying is the up quark and the down quark, that's what the D's and U's stand for. The down quark cannot leave the proton because the up quark is pulling on it through a bed spring. And so we can all understand the mechanism. You know, I don't need to go to college to understand this. This is baby stuff. We can all look at this and say, oh, I understand. I see what they're proposing. But what is the problem? The problem is that the gluon is supposed to be a particle, not a bed spring. That's the problem. And so you say, okay, hold it. Then we have a little bit of a problem because, you know, when you look at the standard model chart of quantum mechanics, you're not going to see pictures for any of the particles, and for sure you're not going to see a bed spring as a physical or pictorial representation of a gluon. They're going to put a particle in there. They're just going to put a letter G and say, that's the gluon, the letter G. So you say, well, what does a gluon look like? And here they're telling you what they look like. They say it looks like a bed spring. And you say, you mean it really looks like a bed spring? And at that point they say, well, you know, we just simulate it with a bed spring. You know, it's not that it looks really like that, but that's the best way we can represent it. But that's misleading because it's lying. It's a total lie because gluon is not a bed spring. And here, let me show you, here's from the science show. It shows the force carriers, which are the gluons. And what do they carry? They carry the strong force. What is the strong force? The strong force is what keeps the quarks tied to each other. As you can see, they're throwing balls at each other. Now, how can the strong force, that little ball that's going between them, how can that keep them together? If I throw a ball at you...
Very easy. If you see three kids playing with a ball, if one walks away, then he's not playing the game anymore. That's what keeps them playing.
Well, you know, this scenario here, and let's put this, the right one here, where was it? Where is it? This one reflects this scenario here. That's that scenario. That's cassemer throwing rocks at the donkey. That's what they're showing there. Okay, so that's what they're representing when they're saying, you know, that the gluons are throwing some kind of gluon ball at the other quark. That's exactly what they're saying here. They're saying, look, here we have the quarks, and they're throwing this little stone at each other and somehow attracting it. And of course, you cannot imagine it here, but you certainly can imagine it here. Here you can imagine it perfectly well because they've replaced the particle that's traveling between quarks with a bed spring. And what I'm referring to here is that this is very misleading. It's showing a mechanism that quantum does not support. Quantum deals with particles, not with bed springs. If they want to talk bed springs, fine. Brings bed springs into the fore. They don't do that. And you're saying, well, where did they get all this stuff? I mean, how can they turn the particle into a bed spring? Okay. And first we have here another group, and they're very popular on YouTube. They're called Cassiopeia. Cassiopeia also shows the quarks inside both the proton on the left side and the neutron on the right side. And what you see there, again, they're kind of floating around. You're saying, well, why don't they leave that sphere that's encapsulating them, that balloon? Why don't they leave that balloon? And what's that smoke in there inside the balloon? Is that just for dramatization, for special effects? What is that smoke going on there? Well, all that is the gluon. And they don't show the gluons going between the quarks, but you can see that the quarks, for some reason, are constrained within a balloon. And again, we look at these things as balloons. And I want to keep that word balloon in there because that's so important. And here's SLAC, the people at the Stanford Linear Accelerator in California. And what do they show? They show particles at the bottom especially. You see the blue quark throwing a gluon at a red quark and changing the color. They use the word color. They've invented this as a property of these subatomic particles. When it throws a quark, when it throws a gluon at another quark, it changes the color of the quark, by which they mean it changes the properties of it. Okay. And by changing the properties, it gives it attractive properties out of the wand of God, because there's no physical mechanism to explain this. So the quark is throwing a particle, and again, this is SLAC, this is official. I'm not inventing this stuff. This is from the Stanford Linear Accelerator, and it shows that a quark throws a particle at a quark, and that little particle is the gluon. And the question is, how does it keep two quarks together? And again, this differs quite substantially or very plainly from, this, the springs. Okay? So we got a problem because we have particles being thrown around, and when the guy says, well, how does it pull the quarks together? And the guy switches his presentation and says, oh, see, here I can show you the mechanism. And you look at that and say, well, I can understand that, but what's that got to do with quarks throwing particles at each other? That's where the contradiction comes in. And that's where you got to stop the guy and says, okay, hold it. I don't understand. The mechanism I understand, but I don't understand how you relate that to discrete particles being thrown from quark to quark. That's where the problem is.
You can't, unless you're throwing the bed springs.
No, and then they don't. Of course.
It's not a bed spring.
Right.
You can't throw
the
something
bed spring
that's
pull.
attaching both of them.
Yeah.
There's a rope between us two. I can't throw it at you.
And I'm sure if I throw a bed spring at you, I won't attract you.
No, but
in any way, shape, or form.
If there's something tying both of us, I can't throw it at you because it's tied to me.
Correct.
So I can't. Mutually exclusive.
I cannot emit it.
Yeah.
And so here they come up with something very funny, which is what my son mentioned a minute ago. And you realize why it's called gluon. They put gluon glue. It's a new product on the market, so I urge you to buy it out there. It can paste any two things together. The gluon glue brings two, in this case, up quarks together. You just pour it between two quarks and it pastes them together. But even assuming there is such a glue out there, is the gluon glue a bed spring? Glue is one thing. And, like my son mentioned a minute ago, I can pull on a cardboard with my back. If you put some glue between my back and the cardboard, my skin and the cardboard, I can pull on it. But is that the mechanism they're proposing, that we're putting glue in there? No, they invented the word gluon, and they got it from this notion of glue, because they're saying somehow the particles are glued together. But it's the mechanism that's missing. Are they glued together by bed springs or by throwing particles at each other? That's what we need to clarify, in the utmost, with the utmost precision when we talk about language. And of course, they're going to say, well, you got to take a course in math at the university to understand what we're talking about. Okay? And again, all the representations here's one from Cassiopeia, also another popular group, and you can see they show the atom and they show the quarks in there, and then somehow they turn them into these bed springs that connect the quarks. And this representation, you'll see it throughout the internet. The fact that the gluons are connected by some kind of extended object. In this case, either bed springs or squiggly lines, whatever you want to call those green things that are uniting the quarks. Okay, so this is a misrepresentation. It's a lie, to be more accurate, which they use to drive home their point. But then it comes another problem. That's here where you see that the two quarks pull so hard on the gluon, they stretch the gluon. The gluon is that sticky stuff in between that stretches, that bubble gum, and it creates two new quarks at the ends. So they're creating matter. They're creating quarks from absolute void. I mean, how did that happen? By magic? How did we create that tiny amount of matter? Imagine every atom doing this inside the protons and neutrons, the quarks moving apart and somehow creating new quarks.
Well, it might not be creating matter. It might be that the new quarks are made from the gluon itself.
Yeah, but I mean, are we creating matter here or not? This looks like creation of matter to me.
But it could also not be.
Okay, show me how it cannot.
Because again, the two balls that get created there
are just inflated by air or what?
No, but the way you're showing it there, it looks like it's being made from the elongated gluon.
Yeah, but look at the end.
Like
why is it ballooning? That's the issue. Why
that's a different issue. But,
no, that's
but it's not creating new matter because it's the same amount of volume.
No, it's not. That's the point. You have a greater volume in the little ball, and the question is, what created that volume? That's what I want to know.
Well, maybe it didn't make extra volume, but I'm saying maybe the new quarks are made of the gluons. That's what I'm saying.
Well, yeah, that's what they're saying. In a way, they're saying that. But my point is that how come that tip suddenly increased in volume? Because that's what we're showing there.
Okay, but it might not be the exact sizes shown here.
Yeah, but the point is they're creating a quark, and you would think that if there are gazillions of quarks between gazillions of gluons, tinier, smaller balls between the bigger quark balls, you would think that all these gluons somehow are being created from the vacuum, and that's why they fill this volume. You know, they balloon because for example, let me give you an analogy.
The gluons are being created from the vacuum.
Well, that's what this is showing to me.
Quarks.
This is what but the
vacuum.
quarks are being created by the gluons, as you well said there. But are we multiplying the number of gluons? Is that why this thing is expanding?
Oh well, again, it might not be that. Like I said, the balls just might not be that big. I don't know.
Yeah, and this is where I have a problem. I don't care how big they are. I'm saying that if they are bigger, even a teeny weeny bigger. That means we created it. It's like, take a balloon, a regular balloon. I inflate it, and the balloon gets bigger. And you say, I know how that balloon got bigger. You pumped air into it. So the air pushed the balloon aside. So we relate the expansion of the balloon to the amount of air you pumped in it. Air is made out of atoms, and atoms pushed outwards. We're all okay. We all can follow the train of thought. Now let's do it with gluons and quarks. We have this gluon tip. We stretch this bubble gum, and suddenly the tip breaks. So the gluon it all converges upon one gluon there, right? There's only very few gluons, and suddenly that expands for whatever reason. I don't care the mechanism, but that expands. What are we saying? We're saying that the number of gluons has multiplied. How else can the density of gluons became bigger, like when you inflate a balloon and push air in there. How else can you explain it? Rationally. Please, rationally.
If you inflate it, I mean, you could just shorten the distance between the quarks. So
but that's not what they're saying. They're saying a new quark is created. They're creating matter from magic.
No, but new quark is created from the earlier gluon But if that is so, there's less gluons to go around, so the distance between the four quarks.
But that's cheating. You know why that's cheating?
Why is that cheating?
Because you're saying there's less gluons to go around. We can all understand that much. Up to that point, no problem.
Well, there's less gluon per pair, basically.
Yeah, but then the question is, we don't have to account for the number of gluons inside a proton or inside a neutron, for that matter. You don't have to account for them. You don't count all the gluons. You say there's lots of them. Okay, so there's infinite amounts. You're drawing from a bank account, from Bill Gates' account. You can draw all the money you want because there's unlimited, trillions of dollars in there or whatever. And this is the same thing. This is like saying, I can borrow all the gluons I want and create quarks because I don't have to account for the number of gluons. And and to some degree, the mathematicians have no problem with that because they say we can create matter out of the vibrating energy of the vacuum.
The ether. We're back to the ether.
Yeah, we're back to the ether. There's this sea of unseen particles, or whatever you want to call them, wave functions out there, equations. And from those wave functions, a particle materializes, comes into the real world. It's no longer part of space. Now it's part of the matter world. And all these gluons just kind of,
it's like there's always more to be taken out
because you don't have to account for it.
You don't have
as long as you don't have to do the accounting, how much you borrowed from here to pay your creditor, no problem. I mean, if you have an open a bottomless pit and you can just draw all the money you want, you can pay all the creditors, no problem. Essentially is what governments do. A bottomless pit, okay? So this is the problem I've got with it. The gluons are created from thin air, and the gluons then, dense up. They become more and more gluons. There's higher density per volume, and that's what creates the new quark. And, as long as you don't have to account for the gluons, or the gluons come from thin air, from thin vacuum, then you can continue this. You don't have to justify it. It's more or less like the issue with relativity, and this is the right context. People say, well, what's outside of Big Bang? What came before the Big Bang? And you say, well, I don't have to account for that because that's unscientific. I have no way of proving it through an experiment. So that's an invalid scientific question. So the buck stops there. And you cannot answer that question because, or you're not allowed to ask that question because the guy's going to say, well, now you're asking some philosophical stuff beyond the purview of science. So stick with science, and they don't account for that. So you never find out what's enclosing space-time. You never have to figure out what came before time, the creation of time, because that's an invalid question. This is more or less the same thing. It's saying gluons bunch up and form a quark, and you have a new quark. Great. What happened to the gluons? Well, it's an invalid question because, see, the gluons come from the energy of the vacuum. And you say, okay, fine. What is energy? What is the vacuum? And then say, well, now you're asking a philosophical question, and you're not allowed to that. And go to the other side of campus. We finished our presentation. Now you go to the other side of campus. So you never get an answer to that question, which is a valid question for rationality. You have to start out with a valid hypothesis. If your hypothesis, if your assumption that you have unlimited gluons is screwed up, then you don't have a theory. You forget about your theory. Let's deal with the assumption before we get to the theory. That's the issue there. Okay, so how do they try to sell this stuff? And this is what I like, and this is the sexual part of my presentation, so I hope you stick around because this is the best part of it. Drum roll, please, here. And here we go. We have this cute little girl, and she's called the physics girl, and she sells this garbage to the world. Now, wouldn't you sleep with this girl? I mean, I would. If they put a gun to my head, I'd have no choice. I'd do it, right? No problem. And, of course, if I had a choice between her and the other guy who sells it on the other channel over here, I mean, which of the two would you select? Would you select this guy or this beautiful girl? Okay, I think it's a no contest. So so you can see how they're trying to sell this stuff. They're putting these girls to try to sell quantum, okay, because they have nothing left. And these are official sites. You're talking about Slack and so on. So how does the physics girl explain gluons, and now we're going to get a little, let's get our microscope and go into more detail here. Why the gluon is looked at as a bed spring or bubble gum or paste or glue or whatever you want to call it. She says you stretch the two quarks. The more you stretch the quarks, the more energy you need to use. That's the issue here. And at some point, the bubble gum breaks, okay, and that's when you created two new quarks. So what is the explanation for the gluon? The gluon comes into being because they're saying that as quarks try to drift apart, trying to leave the proton, trying to leave the neutron, you need more and more energy to bring them apart. And that energy is concentrated in the gluons that serve as mediators, which here again are represented not as bed springs but as bubble gum. So you stretch the bubble gum, and again you see that's a continuous medium there. And yeah, you try to pull the quarks apart and you can't. And we all understand the mechanism. No problem there. I understand the mechanism perfectly well. What's this got to do with gluons being little tiny balls, discrete balls? That's the issue. The issue is that bubble gum there, that bed spring or whatever you want to put, that rubber band there, whatever you want to put in there, has nothing to do with the particle model. So the simulation has nothing to do with with what quantum proposes, particles, discrete particles. That's the issue. And that's her version. Here's another one that you should look at because they have a couple more out there. And this one's done with a rubber band. Okay? And again, you try to shoot a quark out. That's what they try to do at the accelerators. And the quark stretches and stretches and stretches like a rubber band, and it creates two new quarks. Okay? So the simulation is done with a rubber band. So what do we have? We have, let's recap. We have bed springs, we have bubblegum, and we have rubber bands. What do any of those three have to do with discrete particles? That's the issue. And you can see the first, let's see if you can see it again. They use these squiggly lines to represent the gluon, and you'll see it here in a second here.
Yeah, I just saw it.
Let's look at it one more time. See, there's squiggly lines. They show that they're like bed springs, and the question, why do they do that? That's totally misleading. Why don't they portray it as what quantum proposes, particles? They don't do that, and so it's very misleading. And they use the cute little girl to sell it to you. You know, they're selling it through sex. Okay. So here's the French version. I found a French site and I like what they're doing, so I thought I'd include it here. And here you see a representation by the French. Okay, so the hand goes in there, tries to pull one of the atoms out, one of the quarks out, and for some reason the whole thing didn't come out. But anyways, what it does, he tries to stretch the particle out of there, and he finds that it stretches. Again, he uses rubber bands in this case. Unfortunately, I didn't realize that it doesn't show, the pulling. I'll have to put that some other day. Anyway, and what did the French propose? And here you see again the French atom, which is the atom that you're taught in school. And here's the pull, I think. Oh no, again, I don't see it. I don't know what happened here. Okay, so neither one of the two show it. Okay, that part of my presentation's gone to hell.
Less quarks.
Yeah, less quarks. But I can only explain it, and that's that. What they show is that you stretch the quark outside. If you try to pull a quark out of the proton and neutron, the more energy you push, you use to try to pull it out, the stronger the force that pulls it in, or that keeps it bound to the proton or neutron. And that's why it's called the strong force. The gluon is the carrier of the strong interaction. Everybody understood that? The gluon is the carrier of the strong interaction or the strong force. What is the strong force? It's what keeps gluons glued to each other. But it's not really glued. It's that you got a bed spring there. What does the bed spring represent pictorially? That the more you want to pull a quark out, the more energy you need. And that's why they put it as a bed spring, as a rubber band, as a bubble gum. Where did they get this? If you go to CERN, or you go to SLAC or Fermilab or any of these places where they accelerate particles, or so they think, the more you want to break apart the atom, the more energy you need. What does that mean? That means that you need more giga electron volts, or I work with accelerators, but I work with kilo electron volts. These guys work with billions of electron volts. You need billions of electron volts, and that's a measure of energy. So you need much energy, nuclear energy, maybe just blow to smithereens, energy in the side of the sun, whatever you can think of. Very high energy to break these things apart. That's what they conceptualize. And because you need more and more energy to accelerate, as they imagine this, particles around the big circumference, and where they're going to crash them, clash them, smash them together, the two particles, the more energy you need. That's where they get this idea. They say, oh, you need more energy to look at the quark, to see this squiggly thing that we call a quark that comes out of this explosion. So they say you need more energy. Then the gluon is serving as some kind of bubble gum or rubber band, where you need more and more energy the farther the quark is away from its brothers inside the proton or the neutron. And that's where they get the idea. But don't be misled. The gluon is portrayed as a bubble gum. It's portrayed as a rubber band, meaning that the more you stretch it, the stronger you need to pull. And that's where they get the idea that you need more energy, and because you need more energy, they have to represent that as a rubber band and a bed spring. But then they can't reconcile it with particles, discrete particles. And with that, yeah.
One last question. Have you ever done a breakdown for CERN Hadron Collider for the rope hypothesis? Like what happens under the rope hypothesis?
Yeah.
Like why they see these squiggles?
It's very complex, because under the rope model, when they say they accelerate protons or they accelerate electrons, what are they accelerating? Well, what they can measure inside the beamline, which is what that circular thing is called, and which is compressed by magnets, what they're doing really is they have a row of electron shells extending all around. That's what they have. And at the point where they have them twirled, imagine you're twirling your drill bit. Let's just look at it with the analogy of a drill bit. You have a drill bit. It's running a certain speed. Now you ramp it up, and now it's running at a faster speed. And faster and faster and faster. At some point when you got it real fast, you put two drill bits together. Right at the chamber. That's where they take the shots, or they do the analysis. Computer analysis, because they don't see this. It's all done by computers. So you have two drill bits. And they're running at, first they're going slow, and now you're running them faster, faster, and faster. When you get them to the speed that you want them, you put them together and you touch them. Zip! That's what they're observing inside the chamber, and that's what they're analyzing.
But you didn't explain why they see these squiggles.
The squiggles, what are the squiggles? The squiggles, I think, remember, what is the rope? The rope are squiggles. So what they're doing is shaking the atoms of the universe, and the universe and the atom is connected to every atom in the universe.
What do you mean shaking the atoms of the universe?
Yeah, it's a web. You're shaking the web. Shake a spider's web. Just hit it. Hit the poor spider in the middle. Clink, and you'll see the whole thing. If you could film it in slow motion, you would see the whole web shaking. That's what they're analyzing with their computers, with the software. You're shaking the web, a three-dimensional web. Keep that in mind. It's radially, right? But cross-sectional wise, it's a web.
You
And if
need-
you shake the web, the whole web shakes and sends the vibrations all along the web.
And by web, you mean all the atoms that are connected to the atoms that they're looking at.
Of course, if you get two atoms together like they think, they're thinking that they're bringing two discrete atoms and clashing them together, right? Let's assume that what they're really doing is just having atoms all around the torus, because it is a torus, right? And they're all connected, and so you have this electricity going around, because that's essentially what it is. And the higher the energy, that means the more you torque them, the faster the drill bit runs. And now at the point where they meet at the chamber, you put them together, they match the beams, that you match the drill bits, they touch, and now you get that spark. Zip! What is that spark? You move the web, the World Wide Web. We'll see you tomorrow. And food for thought. That's all you can say. Bye-bye.